Okay, so how many of you have heard of standard deviation before? Okay, so let me kind of explain what standard deviation is, because it's the number that I pay attention to almost more than the class average. And I'll give you an example that I think is easier to follow. So let's say I had 2 students in the class, and I had one student get a 0 and the other student got 100, right? Then what would the class average be? 50, right? The average would be 50. I'd add the 2 numbers together, I'd get 50 as an average. Let's say that's average, right? Now, what if I had 2 students, one of them got a 25 and the other one got a 75? It would also be 50, right? And what if they both got 50s? It'd be a 50. So the average, although it is useful, does not tell you whether or not your class is kind of all at the same place or if they're spread out. I think it's obvious that in this scenario, you've got one person that gets it, the other one doesn't, right? Here, there's a little bit of a spread between the 2. Here, at least they're both going down together, right? They're failing together. So this up here, this would have a large standard deviation. All right, and this right here would have a small standard deviation. So what I'm looking for when I look at grades is small standard deviations, which would mean that I have a class that has, everybody's grades are close together, so everybody's kind of on the same page, right? I don't want large standard deviations because that means we've got a group that's getting it and a group that's not. Unfortunately, the standard deviation for this test was a 27.2. Most of my standard deviations in most of my classes historically are about 15 points, about 15. This is 27. It's a huge standard deviation. Huge, almost double what I normally see. And you can see it in the grades. You can see it right here. You know, what we like to see in grades is, and I'm sure you've heard of this, is the normal bell curve. Okay, so you have like your A's here and your F's here and you've got your C's here, right? So you've got basically big group, and I don't say they have to be C's, I'm just saying when it comes to almost anything, right? Whether it be the height of people or how many kids you have, you know, everything has like an average and then there's outliers. There's the people who have 13 kids, right? That's like an outlier. We want, in most cases, you have exceptionally good students, but there's not a whole bunch of them. And then you have students who are really, really struggling, but you don't have many of them. And then you've got like the average, the herd, right? Everyone else just kind of moving along in the middle. That's a standard bell curve. This right here looks like this. Okay, so what we have is people who are getting it, people who aren't, not a whole lot in between those, and then you've got this group in the middle, right? So this is the hardest type of class to teach to because you've got this struggling group right here, right? Probably in here, right? But then you've got these right here. Right? So how do you find that nice middle ground? You still have to challenge these students because they're capable of it. But at what cost? Losing all these? So that was the first test. It's not the end of the road, okay? So even if you fell into this category over here, it's not over. On the other hand, if you were in this category, it's not over either. You still have a long way to go. But unfortunately, you know, the group here, you're going to have some digging out to do. You're going to have to change the way you're studying, the way you approach things. Something has to change. Have you ever heard of Albert Einstein's famous quote of his definition of insanity? Have you all ever heard that? Y'all know Albert Einstein. So Albert Einstein said that insanity is doing the same thing over and over and expecting a different result each time. So you do the same pattern you're always doing, but expecting that something's going to change. That's Einstein's definition of insanity. You have to change something if you want to see some sort of change in change the behavior, and the results should change. So, you know, what do y'all think? What did you think about the test? I'm looking for honest feedback here. You're not going to hurt my feelings.
It was incredibly easy.
It was easy? I find that hard to believe. I'm not disappointed in this. I would be disappointed if I didn't have this group. I would be very, very discouraged. But, you know, we've got a lot of C's in here, and that's good too, you know. I'd be really upset if this was 1, and then I had like real big deviation. What did y'all think about the test? Do you want to talk about comments on it? Did you feel it was fair at least, or yes? Yeah.
I think it was, but there was like a few problems that tripped me up.
Yeah.
It's like I don't know if it's just I didn't understand it, or if there just wasn't enough information given for me to understand. Like the clock one.
The which one?
The clock one.
Yeah, the clock one was tricky. Not a lot of people did well on the clock one.
And number 3, where you just gave us
Mm-hmm.
the graph and then the
Yeah. Yeah, the clock one I figured would give people some trouble.
Other than that, it wasn't terrible.
Nobody made any comments about how good my goat looked. All right, it's the first test. I encourage you again to come by my office if you need help on anything. I've been keeping up with the videos. I have all the videos for the homework for what we're going to do today, what we're going to do the next 2 classes. So I'm almost up to the point where I've got all the videos up through spring break, which is good. So tonight's homework, the video was posted yesterday for that. Yes?
Will you have the solutions for the test? So that we can review them and check ourselves?
I don't mind. I don't want to post them, but you know, if you come by my office, I will make you a copy. But I'm not going to distribute a copy. I'm going to force you to have to come visit me. Does that sound good?
Sounds good.
Okay. Then we can actually sit down and look at it if you want, if you have time. If you can't make my office hours, send me a text or email me, and maybe I can get you a copy of it that way. Anything else we want to talk about in terms of the test? When is our next test? Before spring break, March 1st. Oh, sorry, March 6th. Why did I say first? March 6th. March 6th. Yeah, it's right around the corner. Okay, so the question is, are the tests cumulative? Exam 2 will only cover material after exam 1. However, you know, if I'm asking you to find sine of 30 degrees, that's something that was on exam 1, so you could technically say it is kind of cumulative, but I won't ask you like a clock problem on exam 2. Yeah. And then the final is supposed to be cumulative. If you look at our calendar, we have exam 3, and then we only have 3 classes after exam 3. So the final cannot be just the material after exam 3. It has to be covering, so the final exam will be the core concepts, the most fundamental things coming out of this class that you need to know. We'll discuss that when we get there. Okay. I would say that if you scored less than a 50, I would highly encourage you to come visit me. So we can sit down and we can talk about a plan, where you go from here, what you're going to need to do to achieve the grade you want in the class. You know, we can talk about maybe you're working 80 hours a week and you have 5 kids and you're a single parent and maybe you've got too much on your plate. You know, I don't know. We talk about it. But I'm ready to get into the next section. And that is 7-6. And I have a visual aid here for us. 7-6 is titled Graphs of Sine and Cosine Functions. So we need to just do something real quickly to make sure that we are kind of all on the same page. Right now, if we talk about the six trig functions, right? When I give you something like sine of pi over 4, the way that you come up with that solution is to try and figure out, well, where's the angle pi over 4, right? And then you base your answer, this is the cleanest way at least, figure out where the angle pi over 4 is, and then you're looking for the y-coordinate of that point. And you have to kind of have it memorized what that is. And that would be what? Root 2 over 2. Okay? So everything that we've done so far is based upon either this circle idea or the general like point sitting in space idea or the right triangle idea. That's what all of the ideas behind sine, cosine, tangent, all those have been about, right? Now what we're going to do is we're going to transition into kind of a different perspective on these functions, or on these six functions, and that is, what do their graphs look like? And so when we graph functions back in college algebra, right, graphs of functions. And I'm going to say 1414, assuming everyone knows that that's college algebra. You were given some very explicit functions like f of x equals x squared, and you were asked to graph it, right? And that's one of the ones you should know, right? Coming in here, everyone knows that looks like a parabola, right? And there's a bunch of these. There's a bunch of functions that you should have some basic idea of what they look like. Square root of x. I'll put the little graphs here. This is a little parabola. This one looks like parabola. It's on its side. And there's a whole list of, common toolbox functions, they call them, or essential functions. All of these have an input of x and an output of the function, right? And then you graph it to give you a visual representation of what's happening. That's what we want to do for these functions, sine, cosine, eventually tangent, cotangent, cosecant, and secant. We're going to start with just these two. So to kind of motivate the idea with a visual, I have something for you to look at. How do we go from this circle idea, y-coordinate off of a unit circle, to a graph? Like, where does this idea come from? So let me try and see if you can see this. All right. Okay. So what we want to do is we want to define a new function that's going to go in our toolbox. And it's going to be f of x is sine of x. That's going to be the function, sine of x. Now, the reason why this can be confusing for students is that when we've been doing things like sine of theta, right? Sine of theta, you have the circle again, unit circle, you have some angle here, and then you have an x and y coordinate of the point. This is our unit circle, so radius of 1. When we said sine of the angle, you were looking for the y coordinate, right? Cosine was the x coordinate. But what was being plugged into the actual sine function? Some angle, right? And we called that theta. We are now going to replace the theta with x. Not to be confused with the x coordinate here. X is actually now the angle. And the reason it's the angle is because we've always used x as the input of a function, haven't we, in college algebra? So what I have here is a visual representation of the unit circle, which is something that you should be familiar with, right? And then we're going to be looking at sine of that angle, and that should spit out the y coordinate on the circle. So I'm going to start moving around here. Now watch what happens. Oops, this way. Okay, so right now, I know it's in green, it's hard to read. That says pi over 12. Can you all kind of see that? Y'all see that back there? No? Not really? Pi over 12? Let me see. See if I can change something real quick. It shouldn't take me too long to do this. I got to find where in the code I have that.
HTML. It's like MySpace back in the day.
MySpace? What is that? That didn't help. Hold on, I'm just trying to find, I haven't looked at this code in a while. Oh, there it is. Was that any better? Is that better? Okay. Yeah, hold on. I've got to find that one. It's blue, it's blue, it's blue.
Is that it? Or is this 24?
There it is. It's right here. That better?
Yeah.
Okay. All right. So, if I move this angle to pi over 12, here's my, if I move this to pi over 12, and I try and figure out what the y coordinate is, because I'm talking about sine, it'll be this height, right? So now what I want to do is, that angle is pi over 12. I want to imagine taking that angle and making that my x input. So that's my input. So if my input is pi over 12, I'm right here. And the y value is that height. That's the height of the function there. All right? And then I'm going to do that for all the angles. So as I move to the next angle, pi over 6, see, pi over 6 is my input. It's my x input. The output is the y coordinate off that circle. So it goes up a little bit, right? It's higher than it was. And I continue to do that all the way around. So what's happening as I start to rotate, the y coordinate's getting bigger, isn't it? But it's going to peak out somewhere, isn't it? Where is it going to peak? Right at pi over 2, I'm going to have the highest peak, right? The highest point. That's going to be 1 unit high. But now my angle is going to keep going, right? So my angle is going to keep going, and my y coordinate is now going to come down. Why am I doing y coordinate? Because it's sine, right? Okay. So y coordinate's now coming down. See, the angle's getting bigger, which is why we're moving along the x-axis. And then keep going, and now eventually I get back to pi, right? When I get to pi, I'm now back at 0 for the y coordinate. And now what happens when I rotate down through this way? My y coordinates are going to start getting bigger but negative, right? All the way down to -1. And you go around and you come back, and it takes when you go one full revolution, right? One full revolution, you have completed an entire cycle. You've gone, your y coordinate has gone up to 1, come back to 0, down to -1, and then back to 0. Yes? Okay. Now, if I continue, right, I don't know what's going to happen. Oh, I don't have it. I didn't write the code to go that far. But that gives us one. I'm sorry, I don't remember. Oh, okay, sorry, that's what that does. I don't remember. I should have looked at this before I came in here. This brings all the points in. Okay, so now if we connect all those dots, right, because I just went to certain values, but if you fill in all the points, you get this nice curve, don't you? And that right there is the sine curve. That's what sine looks like.
Will it ever go the opposite direction?
Yes, yes it does. Hold on, let me, oh, I don't need that. So does it go the opposite direction? Let me bring that point back. Let me get that angle back here to 0. Okay, now if I go negative, all that's going to do is turn this down a little bit, right? So as I go down, immediately my y coordinate's going to be negative. So as I go backwards, that's what happens. I get a negative, right? But isn't that value, that y value, how far down I am right here, isn't that equivalent to the angle coming around this way, like that? So it should correspond to the same y value over here. Like those two give me the same y values out, don't they? Agreed? All right.
It's basically flattening out a circle for us to see.
It's kind of, if you want to look at it one way, It's almost like you're starting a clock, and this thing starts turning, and this thing is spitting out how high that point is, right? How high the point is as you start the clock. In fact, I can animate this thing to do that. So it can, you just keep an eye on this y coordinate. That red dotted line matches up exactly with this red dotted line. Like that's how long that is.
And this is using just the unit circle though, right?
This is just the unit circle, which is fine because remember, all the 6 trig functions can be defined on the unit circle. There any? Yes?
So here's my question. Over here you said it's not equivalent to the x value, but I'm looking and it's equivalent to the x value. Am I misunderstanding?
Okay, so let me take you to a point where I think it will be clear. Let's go to this angle right there. Okay? That angle is 2 pi over 3. That's what's being plugged in, right? So 2 pi over 3 is here. It's a positive number. Okay, the y coordinate is about that high, so it's up here, right? But what's the x coordinate at this point? What's the x coordinate of this point? Looks like about negative 0.05 or negative 0.5, right? That's nowhere in the picture. No, it has nothing to do with our picture. This is the angle, and then this is the y coordinate. So angle and y coordinate. Yes? But we've always treated this as our x-axis, right? We've always called it the x-axis. We're not going to start calling it the theta axis.
Okay.
You could, but we're going to call it x-axis because, like I said, when we do all our functions in algebra, x has always been the input, right? Now, the input here is an angle.
Right.
We're going to call it x.
Input is an angle.
The input is an angle, but we're going to call it x. Do not confuse that with the x coordinate on the circle, because that has nothing to do with it. It's the angle of where we are. Does that clarify it?
Like functions, it's just a function.
Yes.
The angle is a function that you're putting it into a function.
The angle is the domain, the input of the function. All right, do we have any questions on this?
Y will never go any lower than what it's allowed to go, right? Like because of that we're using the unit circle.
Mm-hmm. Because of the unit circle, you can see that for the sine function, the highest value it will ever generate is 1, and the lowest will be -1. So the sine function is bounded between -1 and 1. The output, the range, okay, is bounded. Now, this will repeat itself. Once you get back to 2 pi, right? Once you get back here to 2 pi, right there, the graph will continue, won't it? And it will just repeat itself and then keep repeating itself. Every time you go around, it'll repeat. So we call this where it starts and then where it ends. We call that 1 period. Right there, that's 1 period. What's 1 period of sine right there? We call, and this one's a little tricky, but look at the x-axis right here. We have kind of a peak, right, and then a valley. The distance from the x-axis to the peak is what? 1, and distance from the x-axis to the valley is also 1, right? So that distance 1 is important, and that's called our amplitude. So this distance from here to here is called the amplitude. Be careful, the amplitude is not 2, right? Because look, what's the distance from the top to the bottom? That's 2, right? So the amplitude is actually half of that. It's from the x-axis up to the highest point or the x-axis down to the lowest. Make sense? What else? All sine functions in 1 period, all sine functions will have to have 3 x-intercepts. Do y'all see the 3 x-intercepts? There they are. There's an x-intercept.
They have to have 3?
3. X-intercept. X-intercept. Now for a sine function, a basic, this is a sine function, right? This is, you'll hear me say this, this is your like basic sine function. That's like the cookie cutter sine function right there. For a basic sine function, where do those x-intercepts occur? For that first period? At 0, pi, and 2 pi, right? I would like to point out for you, for reference for where we're headed, to remember the two n ones. Where do those happen? At 2 pi and at 0. This is going to become critically important later. 0 and 2 pi are where the two endpoints of the period are, right? Then we have an x-intercept that's right in the middle of those two, right? Okay, remember that. For all basic sine functions, you have 0 and 2 pi, and then you have an x-intercept also right in the middle. There are also two other important points that I want you to see on a sine curve. That's this point and this point, right? Has a highest point and a lowest point, right? And I want to point out where they occur. Doesn't this highest point occur right in the middle of these two x-intercepts? And doesn't this lowest point occur right in the middle of those two x-intercepts? Yes? Now, we could say what they are. They're at pi over 2 and 3 pi over 2, but I'm trying to get you to see a broader picture here. I'm going to try and summarize this with a less detailed picture. Let's say that I have a graph of a sine function. All right? I'm going to put it right here. Let's say that I tell you this is the beginning of the period and the end of the period, and that's all I tell you. What you could now tell me from that is that there has to be another x-intercept, and where is it? Right in the middle, right? Right here, there's another x-intercept. What else could you tell me? I'm going to have a highest point and a lowest point, right? And they're going to be in between these. So somewhere here and here, I'm going to have a highest and a lowest, yes? But what could happen later is that these sine functions can be flipped over. You know, with functions in college algebra, if we put negatives in front, they flip over? Yes? Same thing can happen here. We can have this entire function switch places where it goes upside down, it goes down, then up and back like that. We could have that happen, and it's going to. So, trust me when I'm running through this. If you get it, great. If I just really want to burn this into your brain. If I say I have a sine function that starts and ends right there, here's what you can tell me. There is another x-intercept in the middle. And in the middle of those x-intercepts, I have a point either up here and down here, or down here and up here. Is that fair? We are going to use that information to graph sine functions. Two endpoints, split down the middle, is another x-intercept. Split that in half. You're either up here, down here, and then this one's going to be the opposite. So if this one was up, this one's down. If it's the other way, if this one was down, this one's up. So it's either going to do this, or it's going to do that. One or the other. Yes? Yeah, you could call those maximums and minimums. Absolutely. Yep.
Is it ever gonna get like, I don't know,
Yes.
in size or stretch in size?
Yes, we are going to change the period. We're going to stretch these and shrink them. We're going to move them up and down. We're going to stretch them out vertically. That's why I'm trying to get you to understand this idea of points instead of like 0 and pi. Think of it, look, if I give you two endpoints, you've got a middle point, you've got these quarter, like this is like 4 quarters, right? You've got like first quarter, second quarter, third quarter, fourth quarter, right? So it's like that in one period, you've got these natural breaks within the period that we can help ourselves to graph. All right. Let's try and graph a sine function now, all right? It's not going to be a basic cookie cutter one anymore. All right. And then we'll get to cosine in a little while. So this is our first example. I would like for us to graph y equals sine of 4x. All right, so that's not your cookie cutter function anymore, is it? What's changed in here is the 4, right? The 4. Now, can I just factor that 4 out? Can I just pull this 4 out? Well, let me ask you this. If I told you the square root of 4x like that, can you just pull 4 out as a 4? No, right? This 4 is trapped underneath this root, right? So you can't just like factor it out. This 4 right here is trapped inside the sine, and it does not come out. You cannot remove it, all right? So that 4x is trapped. Everything that you see in here, that entire thing is called the argument of the function. You'll hear me using that language. Okay, so the argument of this sine function is 4x, right? How in the world are we going to graph this, right? How does that 4 impact the basic function? It does something to it. It can't be the same function, right? Has some impact. So are you ready? I'm going to start doing the standard process for graphing. This is the way you should, if you're learning it from me, which most of you are, then this is the way I teach everyone that I ever come across how to graph a sine and cosine function. Right? First thing I'm going to do is I'm going to just remind myself what all sine functions look like. So on the side here, I'm just going to recall that all sine functions look like this. Basic sine functions. 2 pi, pi, 0, right? And that these are natural quarter marks where these peaks and valleys occur, right? That's what my basic sine function looks like. Well, this one with the 4 inside is definitely different. It's definitely different. Something has changed. So what I'm going to do first is I'm going to try and figure out where these 2 endpoints are for that function. And to do that, the standard technique is to take your argument and set it equal to 0 and 2 pi. That's the standard approach. So I'm going to, step 1, set argument to 0 and 2 pi. Now, why am I setting it equal to 0 and 2 pi? Well, would you agree that when this is 0, I'm going to be here? And when this is 2 pi, I'm going to be here? Yes? So I need to figure out what will make that 0, what will make it 2 pi. So I'm going to set 4x equal to 0, and I'm going to set 4x equal to 2 pi. I have 2 separate equations I'm working with here. You see them? Now, what is the solution to the first equation? 0. Just divide by 4, you get 0. So that's one of my endpoints to the period. Now divide the other one. You just get pi over 2. So you're doing 2 pi over 4. This is pi over 2. All right? That is the first, well, this is the first step, I guess, is to remember what it looks like, right? You set the argument equal to 0 and 2 pi. Now, I'm going to go to the graph. You ready? Here's how I do it. I know now that I have an x-intercept at 0, and I know I have another x-intercept where? At pi over 2. And because this is a standard sine function, I know I have another x-intercept where? Right in the middle. So it'd be nice if I knew what that middle point was. Do I know what the middle point is? Pi over 4. So how are you getting pi over 4? A half of pi over 2, right? Okay. That's because this is 0, and that makes it easy to figure out what half of this is. But let's remember, because this is going to come up, how do you find the number that's in between 2 numbers? add them, and divide by 2. You take their average. Do you all hear me? Okay. So I'm going to do that on the side. Even though we all know this is pi over 4, I'm going to just practice this. I take 0, I add pi over 2, and I divide by 2. This is pi over 2 divided by 2, right? 2 is the same as 2 over 1. And then you reciprocate this. And that becomes pi over 2 times what? When I say reciprocate this, I mean bring that up, turn division into multiplication. It becomes 1 over 2, and then you multiply straight across pi over 4. Is everybody clear on this? Are you sure? Because these things are not going to be as easy as pi over 2 in a second. We're all right? Okay. So this is pi over 4. And what do I know I have here? An x-intercept. I forgot to put this x-intercept here. All right. What else do I know must occur on the sine function? I've got some peak, right, and some valley here, some highest and lowest point. And where do they occur? In between those, right? So I actually need to figure out the halfway point here and the halfway point here. So I need to find the halfway point between these two. So I add those two together and divide by 2. And what would you get? If I take this one and add this one, I just get pi over 4. And then divide by 2, and I get pi. Do I need to do it? You get pi over 8. I'm going to erase this over here. I've got this done. I'm going to go through these, all right, because in my experience, the part of graphing that students mess up the most is figuring out what these points are. They can get the picture, but they can't figure out where these points are. And that you have to be able to tell me where those points are. So I'm going to find this point right here. To do that, I take 0 and pi over 4, I add them together, and I divide by 2. That's pi over 4 over 2 over 1. Division is the same as multiplication of the reciprocal, so that flips, and I get pi over 8. So this is pi over 8. We good? How about this one right here? I have to add these two and divide by 2. I'm going to do that over here. So I'm going to take pi over 4, I'm going to add to it pi over 2, and I'm going to divide by 2. Now if I add pi over 4 and pi over 2 together on the top, I must have a common denominator, right? So that means this has to have a 4. So I'm going to multiply top and bottom by 2. So this becomes pi over 4 plus what? 2 pi over 4, right? And then over 2. Now, what is the numerator? What's pi over 4 plus 2 pi over 4? 3 pi over 4. Right? So if you're adding fractions, if they have the same denominator, you keep the denominator, you add the numerators together. Now, I'm going to divide that by 2, which is 2 over 1. This flips up here and becomes 1/2, and we get 3 pi over 8. Okay. Is that all right? I realize that some of you could have just looked at that and got that. But I'll give you one little while where you won't be able to. No one in here will be able to look at it and just tell me what it is. All right? Okay? Now, I know now that my graph either looks like that or like that, right? I'm not quite sure which one it is. So the only thing left for me to do is determine if I have a point up here and down here, or down here and up here. And then I can just connect the dots knowing what the shape of it should look like, right? So how do I determine that? Negative, positive, where? Out here? So some of you have learned that you just look at the number out here. If it's positive, it'll look like that, the solid one. If it's negative, it'll look like the other way, right? Dangerous. It's dangerous. It's dangerous later. It's dangerous 2 sections from now. Right now, I think it works, okay? But I'm not going to teach it that way because it's dangerous. If I do a proper shift, phase shift, I can make that not work the way you think it's going to work, okay? So the fail-safe way to do it is to just check. what happens if I try and plug pi over 8 into the function? It's going to spit out a point, isn't it? Let's see what point it spits out. All right? So I'm actually going to evaluate this function at pi over 8. So I'm going to take this, y is equal to sine of 4 times, and I'm replacing x with pi over 8. And now the 4 and the 8 reduce out, don't they? I mean, like this 4 once and 4 twice. So this is really sine of what? Sine of pi over 2. And now we're back to the unit circle. What is sine of pi over 2? So you go, pi over 2 is straight up. Sine is the y-coordinate. The y-coordinate up there is 1. So isn't this a 1?
So when we do that, is that always going to tell us what's up or what's down?
This will, yes,
So
because
it's either always going to be pi over 2 or...
it should turn out to be either pi over 2 or 3 pi over 2.
Yeah.
It's going to be one of those. But it could also be some multiple of those. So like it could be pi over 2 or add an entire rotation and be back there. So it could be like, hold on. Sorry. 5 pi over 2? Sorry. It could be 5 pi over 2, which would give you the same result. So I know that when I plug in pi over 2 into this function, sorry, not pi over 2. When I plug in what into this function? Pi over 8 into this function, it spits out 1. So when I'm here at pi over 8, I go up 1 and I draw a dot, and that's 1 unit high. Okay? Because it's a sine function, you do not have to test 3 pi over 8. You know that this one is going to be the opposite. So on this one, you come down -1 and you put a dot. And now you're back in kindergarten. You're just going to connect the dots. Now, when you connect these dots, it has to still look like a sine curve. You can't just do whatever the heck you want, all right? So this point right here, when you connect these two together, I want you to look at this when you draw it as the left side of a frown. Happy face, sad face. Left side of the frown is this picture. It's not straight. It's not a straight line. It is the left side of a frown. From here to here is the right side of a frown. How about from here to here? Left side of a smile. And from here to here, right side of a smile. That right there will give you full 100% credit for that exercise. I can see the amplitude. It's marked, right? I can easily distinguish what the period is. The period goes from 0 to pi over 2. And I can easily pick off where all the important points are. What do you think? Yes?
I got a little confused on how you got equals 1.
Equals 1? Okay, so when we get to this point right here, right there, you have to go back to your knowledge of the unit circle, which is what we did the class before the test, which is if you're on the unit circle and you go to pi over 2, and you're asking what sine of that is, you're looking for the y-coordinate here, which is 1. That clear it up?
Yes.
Okay. Any other questions before I proceed to the next example? All right? All right, we're just going to change up the argument. Well, I'll do a little more than the argument. Let's do something else. Let's do -3 sine of 1/4 pi x. So I'm kind of throwing you into the fire here. Does that look a little more complicated than just your standard basic cookie cutter sine function? You got more going on here, right? You got negative 3 out in front being multiplied. Inside the argument here is a little more complicated. It has a pi in there. It's a fraction. All right? But at the end of the day, we know that all sine functions have 3 x-intercepts, right? And then these quarter marks where I can pick off the high and low points, right? And that's what I'm going to go after. So how do I pick up these two endpoints? Set the argument equal to 0 and 2 pi. You do that every single time with sine. All right? And there's good news. When we get to graphing cosine, you do the same thing, 0 and 2 pi. Bad news, when we get to tangent and cotangent, they're not 0 and 2 pi anymore. This only works for sine and cosine. All right, so I'm going to set my argument, just the argument, 1/4 pi x equal to 0. The other one, 1/4 pi x equal to 2 pi. We good? Now you solve those. The first one is just 0. And the second one, you can divide both sides by pi, right? And they're gone. And how do I get rid of 1/4 in front of x? Multiply by 4. Both sides by 4. And what are you left with? 8. X is 8. Huh, weird. You know how in the previous problem, like all my little dashes on my axis had pi's in them and stuff? This one doesn't. These are nice little integers. This might make it a little easier to graph. I know that I have one x-intercept at 0, and I know I have another x-intercept at 8. And I don't think we're going to need to do any computations for these midpoints, I hope. Yes?
Is that x-intercept always going to be 0?
No. The question was, is this x-intercept always going to be 0? The answer is no. Now, it will be today, but it won't be when we move into the next two sections. We're going to have what are called phase shifts. So we're going to take this graph and we're going to move it left or right. And then that x-intercept is not guaranteed to land at 0 anymore. If you have this right here, without another number in here being added, so like in order to shift it left and right, I'm going to have to add or subtract a number next to this. If it's not there, then yes, you will have one at 0. All right, so I now need to, I have those two endpoints. I need to go pick up those other points. I know a middle point, and I don't need to do the computation. That's going to be an x-intercept. And then those two cut in half. Fortunately for us, again, those are easy to see, right? That's 2 and 6. No computation required. And now all I need to do is figure out whether or not I'm up here and down here, or down here and up here, right? That's what I'm going to now determine. So how am I going to do that? Plug 2 into the function. Did you say or 6? I don't have to do both.
Oh, that's right, that's right.
Because I know it looks like this. It's either going to go up and down, or it's going to go down and up. So you only need one. Okay, that's good. If you want to do both, you can, but you only need one. Could I have done 6 and not 2?
Yes.
Yeah, it doesn't matter which one of these I do. So I'm going to just pick 2. Just be careful. Don't pick 0, because if you pick 0, what's going to come out? 0. If I pick 4, I'm going to get 0 out. If I pick 8, I'm going to get 0 out, because those are x-intercepts, aren't they? So I'm interested in what's happening at 2 and 6. So I'm going to plug 2 in. Where am I plugging into? In for x, into that, right? Okay, so I have y equals -3 sine of 1/4 pi times 2. So I replace that x with 2, and that's just pi over 2, isn't it? 2's reduce out. You get sine of pi over 2, but what's sitting in front of that? -3 sine of pi over 2. And sine over pi of 2 is 1. Right? Sine of pi over 2 is 1. 1, 2, pi over 2. So this is going to be -3 times 1, which is -3. Questions on that? Yes?
Whenever we're graphing them, do you want us to tell you what the amplitude is?
I will, yes. When we get to the final section of this, I'm going to give you a sine function. I'm going to ask you to graph it. I'm going to ask for the amplitude, the period, and the phase shift. For now, let's just get these graphs down. Let's focus on getting our points right, testing our points right. We'll get to all that stuff later. Okay, so now I have an idea of how big this needs to be. At 2, I should be at -3. So I'm just going to put a point down here. I'm going to mark it as -3. And then what does that mean is happening at 6? It should be +3. So +3 would be, I don't know, about right there. I mark it over here as +3. We good? That should be enough, right? So now I draw very jagged, straight edges like that, right?
Yeah, do a happy face.
Do happy face. So I'm going to do this happy thing and then sadness. I don't really like that. That doesn't look good. That should be the highest point there. All right, good enough? We okay with that? Are you sure? No questions. You're all experts now? Okay, what if I asked you to graph 2 periods of this function?
Keep going.
That means I want another one. Let's see how easy this would be, if it would be easy. So if I did this and continued this out, do we know the distance between here and here? It was 8, right? So that means I could continue this out to 16, and then I could go halfway. What would halfway be there? 12? And then what would half and half there be? 10 and 14? And then I know that I have x-intercept in the middle and at the end, right? And then it's going to continue the same pattern. So it's going to come down, back up, and back down. Now, it was easy to get 16, 14, 12, and 10, wasn't it? Because the numbers were real nice here. But if they weren't, you could still do this. You would just have to do a lot of averaging of numbers to do it, which is part of the headache with these problems, is that part, getting those x values.
So, like, amplitude is always positive?
Yes, your amplitude is always positive. But I haven't defined it for you yet. And I've told you it's this height, right, which is 3, which would be, it's -3 here, but when we talk about amplitude, we take the absolute value of that number. But I'll give you that in a formula later. I just really want to focus our attention on what's the process we have for graphing. What's it going to be? Okay. Now I'm going to give you one that's not so natural, all right? Something that's a little bit more, forces you to really mess with numbers. So how about this? Let's go 1/10 sine of 7x. It's a sine function, right? Has 2 endpoints that are x-intercepts. It has a middle point that's an x-intercept. What do I do first? Set the argument equal to 0 and 2 pi. First one is just 0. Second one, 2 pi over 7. Now I'm going to mark this x-intercept at 0, and I'm going to mark the other one here at 2 pi over 7. And notice, like, I'm just giving myself enough space to draw my picture in here, right? Like I could put 2 pi over 7 out here. It doesn't matter where I put it. What next? Find the middle. To find the middle, I add the 2 up. What is 0 plus 2 pi over 7? Just 2 pi over 7? And then divide that by 2 over 1. 0 plus, what is this? Just pi over 7. I don't want to like shortchange y'all by not showing you all the detail, but I also don't want to insult you. I mean, this is, yes? Pi over 7? Okay, so pi over 7. Let's go ahead and mark the x-intercept here. And then let's grab these two. So what's the one between the 0 and the pi over 7? Pi over 14. Okay, pi over 14. And do you feel like you could get this one on your own? Feel like you could put these two together and do it? So what is it? 3 pi over 14. We good? Are you sure? I want to show you a very slight shortcut, but I don't like this shortcut because it only works if your x-intercept starts at 0. Once we start doing phase shifts, it doesn't work as well. But I'm just going to point it out. From here to here, you're jumping by how much? How much did you move from here to here? It was pi over 14, right? One jump of pi over 14. This would equate to taking how many of those jumps? 2 jumps of pi over 14, right? And what would that become? Pi over 7. And then this would be my 3rd jump of pi over 14. And then this would be my 4th jump of pi over 14. And that reduces to be what? 2 pi over 7. You see that? You can actually kind of check that you did it right. Like pi over 14, 2 pi over 14, 3 pi over 14, 4 pi over 14.
So basically, we don't have to go through all the math.
Only if you start at 0. Yeah. Well, you still have to get pi over 14, right? But that one was, yeah, I mean, yeah. It's just a little cute little thing you can do to check, or if you want, use as a shortcut. All right. Now, what am I doing? Plugging in pi over 14 into the original function and seeing what comes out. All right, so when I do that, I take 1/10 sine of 7 times pi over 14. And man, that keeps on popping out, doesn't it? Pi over 2, sine of pi over 2 is 1. So this becomes 1/10, don't forget about that 1/10 times 1, which is 1/10. So that means my graph is up 1/10, right? So you could just like put a little tiny, or just put it here, mark it as 1/10, that's fine. Look, when we draw our x and y axes on a graph, they do not have to be scaled. In other words, when you draw, normally you do like 1, 2, 3, and then you do the same distance, like 1, 2, 3, right? Like this is 1 here, that's 1 there. That doesn't have to be that way. You could, if you wanted, have these be 10, 20, 30. You can change the scale. Like what's 1 here does not have to be 1 there. What you cannot do, though, is make this 1 and then 2 and then make it 30. That doesn't make sense. You can't change the scale in the middle of the same axis, all right? So I'm going to